So let's solve Cambridge International AS and A Levels Chemistry, Paper 1, Multiple Choice, February, March 2025, Paper 12. First question states that a Boltzmann distribution for a sample of a reacting gas at a constant temperature is shown. The activation energy EA for the reaction is marked. Point cross shows the number of particles whose energy is equal to the activation energy. So basically, this point is showing the number of particles whose energy is equal to the activation energy. So that means all the particles that are going to be on the right side of this point are going to have greater than activation energy, and all the particles that are going to be on the left side are going to have less than activation energy. Okay, the temperature of the sample of gas is decreased, so now you're going to decrease the temperature, and you know that whenever you are going to decrease your temperature, what's going to happen to the Boltzmann distribution curve? It's going to shift towards the left side. So now the new curve is going to be a little higher and something like this. Okay, what happens? The peak increases when you decrease the temperature, and the main part, the most probable particles, this part, basically this initially it was this part, now it has shifted towards your left side, which is this part. Okay, which point could show the number of particles whose energy is the same as the activation energy at the new temperature? So now, firstly, you know that there's a very important line over here that you should write. Only catalyst can change activation energy. That means that nothing apart from catalyst in our syllabus can change the activation energy. Over here, what they have done is they have decreased the temperature. So despite decreasing the temperature, the activation energy is not going to be disturbed because only catalyst can change it. So what's going to happen? The activation energy is going to remain on the same line. So either it's going to be B or it's going to be D. Since I told you that when we decrease temperature, the curve shifts towards this side, and this line becomes lower. So I've just lowered it a little more. It can be here as well. It becomes lower than the original line. This was the original line. Now this is the lowered line. So it is going to be option number D. When you decrease the temperature, this is going to be the number of particles that are going to have your energy greater than equal to the activation energy. Okay, and this is your activation energy, which is going to remain the same. So I hope you got it. Option number D. Crystals of copper 2 nitrate are prepared by adding excess malachite to nitric acid. So you have malachite, you're adding it in excess to your nitric acid. The formula of malachite is CuOH2 and CuCO3. The MR of malachite is this. 12 gram of malachite is added to 30 cm cube. Now you know that your malachite is in excess. Okay, so the mass of this thing is not going to determine the mass of your product. Only the mass or the moles of the limiting reactant are going to determine your product, right? 30 cm cube or 1.5 mole per dm cube nitric acid. Which mass of malachite is left unreacted when the reaction is complete? Okay, over here, what do you have to identify? You have to see that what is reacting with your nitric acid. So over here you have copper hydroxide and you have copper carbonate. So first let's make copper hydroxide react with nitric acid. So you have copper hydroxide, and when it's going to react with HNO3, which is your nitric acid, we have a base, we have an acid, we're going to form CuNO3 copper nitrate, plus we're going to form copper nitrate plus water, right? H2O. And then what are you going to do? How many waters do you have? You're going to put a 2 over here. to balance this out, and a 2 over here. Are we balanced? Yes, we're balanced. So that's the equation of copper, of your nitric acid, because look, malachite is not a proper compound. It's like it has two compounds in it, copper hydroxide and copper carbonate. So you have to take into account both of them. That's what I think. So let's proceed with this question, see are we doing it right or not. So that's the first equation for copper hydroxide that I have formed. I'm going to form another equation with copper carbonate. So over here, let's see what happens with copper carbonate. If copper carbonate and you add your nitric acid to it, what are you going to form? You're going to form copper nitrate first, and then you're going to form carbon dioxide, and then you're going to form water. Put a 2 over here and you're good to go. So that's the two equations. Okay, so now 12 gram of malachite is added to 30 cm cube of 1.5 mole dm cube of nitric acid. So we got to check how many moles of nitric acid do we have, and then we're gonna, from that we're gonna check how many moles of this malachite thing are gonna react with it. So over here we can see that if we have 2 moles of nitric acid, they react with 1 mole of copper carbonate, and over here 2 moles of nitric acid are gonna react with 1 mole of copper hydroxide. So let's figure out the moles of nitric acid. So there are gonna be 30 cm cube divided by 1000, because we take it in dm cube, multiplied by 1.50. 30 upon 1000 multiplied by 1.5, and I get 0.045 moles. 0.045 moles of nitric acid. Now I know one thing, that if I have in total 4 moles, like 2 over here and 2 over here, right? If I have 4 moles, I'm gonna react with 1 mole of malachite, because 1 mole of malachite contains 1 mole of copper hydroxide and 1 mole of copper carbonate. So over here I can consider this to be 1 mole of copper carbonate and 1 mole of copper hydroxide. So in total, this and this tells me that 1 mole of malachite is going to react with 4 moles of nitric acid. 2 over here, 2 over here. So I know that my malachite, which is copper hydroxide, copper carbonate, ratio HNO3 is 1:4. Okay, so now if I have 0.045 moles of my HNO3, which is 0.045, I'm gonna have X moles of malachite. How many moles of malachite would come? We're not basically calculating the moles of malachite, we're just calculating the combined like moles of this and this. So don't consider it to be a different compound like malachite, consider it to be copper carbonate or copper hydroxide. So what do we get? We get 0.045 divided by 4. How many moles are we getting? Divided by 4. 0.01125 moles of malachite. Now what do we need? We don't need the moles. We need the mass, right? We're dealing in mass. So now we have the reacted moles. So we can calculate out the reacted mass. What's the formula for mass? I guess that's very clear, that mass equals to moles into mR. These are the moles. We're going to multiply them with the mR. They've given us the mR, which is 221. Multiplied by 221. What kind of mass do we get? We get 2.48625 grams. So basically these are the reacted grams. Okay, these are the reacted grams, and we got to calculate the mass of the unreacted one. So now we're gonna subtract the reacted one from the total mass, which was 12 grams. So that's simple mathematics, I guess. It's going to be 12 minus 2.48625. 12 minus 2.48625. And what do we get? We get 9.51375 grams. Okay, so that's our answer. And correct to three significant figures, it's going to be 9.51 grams, which makes this the correct one. Okay, I hope you got it. It was a little complex, but like not very hard, but there was like a good amount of working required. So done. Next, X and Y are elements from this same group of the product table. The 5th to 9th ionization energies of X and Y are shown. So when we know that they're belonging to the same group, we know that the big jump is going to be from the same ionization energy to the same ionization energy, because when you're in the same group, you have the same number of electrons in your valence shell, and when you have the same number of electrons, the big jump's going to be same. So from 11,000 to 15,000, not very impressive. From 15 to 17, not very impressive. From 17 to 92, look, there's a very big jump from your 7th to 8th ionization energy. Can you see the big jump? Yeah, I can see it. Then I'm expecting that in my element Y as well, the big jump is going to be from 7 to 8 because they belong to the same group, right? So 11,000 to 33,000. That's impressive. That's a big jump, I guess. Which row identifies elements X and Y? So now I know that firstly they're both going to belong to the same group. So I cut out the options that have different groups like argon and neon. And I know they're going to be in the seventh group. Why? Because the big jump is from 7th to 8th ionization energy, which means that the last shell has 1, 2, 3, 4, 5, 6, 7 electrons. And the inner shell can have like multiple electrons. Like if that's the inner shell, I don't know how many are going to be there, but like I know one thing for sure, that the 7 electrons are going to be removed from the last shell, and then the 8th electron is removed from an inner shell. That's why it's greater, because the shell is closer to the nucleus, so the nucleus is pulling it more tightly towards itself. That's the concept here. So definitely we're not dealing with argon and neon, and we're not dealing with argon and neon. We're dealing with chlorine and fluorine. Now we got to identify which is going to be chlorine and which is going to be fluorine. Now you got to realize one thing. We know for sure that fluorine has 9 electrons. Okay, so if I try to draw fluorine, so if I consider this to my fluorine, then I'm gonna have 2 electrons in the inner shell, something like this, right? Fluorine is 2, 7, right? That's the electronic configuration for fluorine. And now if I try to draw your, chlorine, it's gonna be, we add a Cl here, we add one more electron, and then we add one more shell to it, something like this. And chlorine is gonna be, what's chlorine? Chlorine is 2, 2, 8, and 7. So 1, 2, 3, 4, 5, 6, 7. Now when you see this, you realize chlorine has a bigger size and fluorine has a smaller size. When the 7 electrons of fluorine are going to be removed, okay, when they're going to be removed, the 8th electron of fluorine is going to be removed from here, right? From here. This is the nucleus, and the 8th electron is going to be removed from here. But in chlorine, when the 7 electrons are going to be removed, the 8th electron is going to be removed from here. at this position and the nucleus is here. Now check it for yourself. In fluorine, the distance between the 8th electron and the nucleus is less, right? The distance between the 8th electron and the nucleus is less. In fluorine, the distance between the 8th electron and the nucleus is more. So that means fluorine is going to have a higher 8th ionization energy compared to chlorine. And you know that when we come down the group, consider it to be the group like fluorine, chlorine, the ionization energy decreases. So this element which has a lower 7th to 8th ionization energy, lower like from 17 to 33, is going to be chlorine, and the one which is higher is going to be fluorine, because we know down the group ionization energy decreases. Across the period, ionization energy increases. So this element Y is going to be your chlorine, and the element X is going to be your fluorine. Okay? So that's the concept. An ion with a charge of 2 negative contains 10 electrons and 14 neutrons. What is its nucleon number? Okay, it has a 2 negative charge. That means out of those 10 electrons, 2 electrons are gained, right? 2 electrons are gained. So what are we going to do? We're simply going to do 10 minus 2 equals to 8 electrons. So initially it had 8 electrons, a neutral atom. If it had 8 electrons, it would have 8 protons as well. And if it has 8 protons, initially 8 protons plus 14 neutrons is going to give me the nucleon number. So 8 plus 14, that gives me 22 nucleons. The structure of hormone histamine is shown. So we have histamine here. That's angle X, that's angle Y, that's angle Z. Which row contains the bond angles X, Y, Z in histamine in the correct order from the smallest to the largest? So let's figure it out. We know that whenever a carbon atom makes one double bond, whenever a carbon atom makes one double bond, or a carbon atom is sp2 hybridized, and its bond angle, like it makes one double bond like this, it's 120 degrees. Yeah, we know this. So over here we can see this carbon atom making 2 single bonds and 1 double bond. We know that it is sp2 hybridized, hence this bond angle, and this bond angle are all going to be 120 degrees. Then now we can see this carbon atom is sp3 hybridized, since it's making 4 single bonds. So this fellow over here is sp3 hybridized, and when we know carbon is sp3 hybridized, the bond angle is 109.5 degrees. This nitrogen atom over here, it's making 1, 2, 3 bonds, and it has a lone pair on top which you cannot see because it's missing over here. But that does not mean it's not present. So you have a lone pair sitting here, and the lone pair is basically pushing the bond pair, repelling the bond pair downwards. So this angle, if this lone pair was a bond pair, initially nitrogen would make 4 bond pairs and the angle would be 109.5. But now we have a lone pair here, which is going to push this more downwards. So minus 2.5. That's 109.5 minus 2.5, 107. So it's going to be 107 degrees. We subtract 2.5 because of this lone pair that's pushing them down. So this is 107 degrees. So we have to go from the smallest bond angle. Smallest bond angle is going to be X, and largest is this Z. This is 120 degrees. Y is going to be 109.5 degrees, and X is 107 degrees. When an organic acid reacts with an alcohol, a reversible reaction takes place, producing an ester in water. 0.4 mole of an organic acid and 0.3 mole of an alcohol are mixed and allowed to stand at 25 degrees until equilibrium is reached. At equilibrium, zero point 0.2 mole of ester are produced. What is the value of the equilibrium constant Kc under the conditions used? Okay, so they're saying we have an organic acid plus alcohol and we're producing an ester in a reversible reaction. Okay, so first the initial moles are of organic acid are 0.4 moles. For alcohol they're 0.3 and for ester they're 0. Okay, at equilibrium 0.2 mole of the ester are produced. So now the change in moles we don't know right now, but the equilibrium moles we know that for the ester they are 0.20. So you know that if 0.20 mole of ester are being produced, okay, so the change over here is going to be positive 0.20 because these many moles of esters are produced, and the ratio between the ester and the alcohol and the organic acid are 1:1:1, right? 1 mole of organic acid, 1 mole of alcohol, 1 mole of ester. So if 0.2 moles of this ester are produced, 0.2 moles of the alcohol are going to be used and 0.2 moles of the acid are going to be used. So now if we subtract 0.2 which are used from the initial moles, let's find out the equilibrium moles. So over here it's going to be 0.20, over here it's going to be 0.10. Okay, so now we got hand of the equilibrium moles of all three. Now what's going to be the Kc expression? For the Kc expression we write the products on the top. So Kc, we write the products concentration divided by the concentration of the reactants. Okay, so over here we are not given with the volume. Since we're not given with the volume, we cannot figure out the concentration, so we're going to consider moles to be the concentration because we can consider that we have 1 dm cube of volume. So products are ester, which is 0.20, upon the reactants are 0.20, which is the acid, and 0.10, which is the alcohol. Let's check out what do we get. 0.20 upon 0.20 times 0.10, and I get 10 as my answer. So just realized a small mistake I was making over here. It was the moles of water. We didn't consider water, and I just realized how can I get like 10 over here, like that's a really big value. And I realized looking at the marking scheme we missed the moles of water. So 0.2 moles of water are also going to be formed, okay? And that's a very tricky thing. In esterification you got to remember water formation, and I personally just forgot it. Like you have an acid, you have an alcohol, it's going to react to make an ester and water. So over here we're going to add the moles of water as well, which are going to be 0.2, and when we're going to solve it, then we're going to get option number C as an answer. So don't forget the moles of water, they're really important. I know such things just like are like not genuinely easy, like because they're gonna slip out of your mind out of nowhere. So just write a point that in esterification, I know majority of you guys must have forgot it. In esterification, water is formed as a byproduct. Okay. Information about two substances are given. We have a substance P, which is good when solid and when molten. So we're talking about a metal over here because only metals are good when solid and molten. If we're talking about an ionic compound, they're not good in solid. Effect of adding water: reacts vigorously to produce an alkaline solution. We're definitely talking about either it's a group 1 metal or a group 2 metal, and the melting point is 454. I think a group 1 metal. I just think like it can be anything, but definitely over here we're dealing with a metal. For substance Q does not conduct in any state. If it does not conduct in any state, then either we're talking about a simple molecular or we're talking about a giant molecular structures, because they don't conduct under any conditions, react vigorously to produce an acidic solution. So we're talking about two substances, a substance that react vigorously to produce an acidic solution. Okay, we know that acidic solutions on adding water, non-metallic oxides, non-metallic oxides or hydroxides, not oxides but non-metallic substances produce acidic solutions. So over here we're talking about some non-metallic thing, and definitely P is gonna be giant metallic and Q is gonna be simple molecular. We're talking about a simple molecular substance, and probably we're talking about an oxide or an oxide or a chloride of the non-metals, like either it can be PCl5 or we're talking about P4O10, something like this, because they're gonna react vigorously to produce an acidic solution. P4O10 gonna form phosphoric acid, PCl5 also gonna form your acid. So I think that's something like this. So option number A, though we don't have to guess, but we should be mindful of what's happening. An excess of zinc An excess of our zinc reacts with xCm cube. We don't have the volume of 2 mole HCl. Let's just produce an equation. We don't have to produce them. We just have to learn them. We have zinc. We have HCl. What do we form? We form ZnCl2. Don't forget this 2 plus hydrogen gas. So we have a solid here. We have aqueous here, we have an aqueous solution here, and then we have a gas here. And then the meaning of the equation was 1 mole of zinc gonna react with 2 moles of HCl. Okay, now the gas produced is dried and collected. The gas occupies this much dm cube of this much pressure at this much temperature. The gas produced behave as an ideal gas. What is the value of X? No worries at all. So first things first, we got to calculate the moles of H2. We know the formula PV equals to N or T. We got to find the N, which is the number of moles. Pressure is 101,000. Volume is 1.534 dm cube. We got to take it in meter cube in this equation. So into 10 raised to power -3. These are the only petite, small, tiny things that cut off your marks. Like this esterification thing over here. It's such a small thing that water is produced. We all know water, but we just like tend to forget these things and we just lose hold of our marks. So over here, it's PV equals to N times R. R is the general gas constant, which is 8.31 times the temperature, which is 293 Kelvin. If we arrange it, what I've done, if we arrange it, R and T are gonna come down here, and then there's gonna be a line in between, equals to N. So let's plug this in our calculator and let's see what do we get. 101,123 times 1.534 into 10 raised to power -3 upon 8.31 into 293. What do we get? N is coming out to be 0.0636 moles. Now I know that I need the moles of my hydrochloric acid. If I have these many moles of this, the moles of my acid are going to be double because there's a 2:1 over here. Okay, so if I make the mole ratio over here, HCl ratio H2, so I know that double of my moles are going to react. So multiplied by 2, we get 0.1272 moles of our HCl. Up we have the HCl moles. What do? Now we got to find the volume. We simply know that moles equal to our volume times our concentration. So moles are 0.12726 divided by the concentration, which is 2, is going to give me the volume. Divided by 2, I get 0.06363 as my volume, which is in dm cube. I need it in cm cube, so I divided by, not divide, I multiplied with 1000 and I get 63.6 as my answer. I get 63. This is gonna be multiplied by 1000 and I am getting on calculator 63.6. So this should be the correct answer. I hope you got it. We just had to make equations and manipulate stuff. Okay, an aqueous solution of hydrogen peroxide is placed in a flask and decomposes as shown. So we have hydrogen peroxide, which is decomposing into water and oxygen. 2 moles of this. Equations are just for the mole ratio. Forming 2 moles of water, forming 1 mole of oxygen, and total volume of oxygen gas evolved is 180 cm cube. So we have a total of 180 cm cube of oxygen gas after 90 seconds. So after 90 seconds, we have a total of 180 cm cube of oxygen measured under the condition. The rate of the reaction is change in H2O2 moles divided by the time. Okay. What is the average rate of decomposition mole per minute over the duration of the experiment? So we got to calculate the change in moles divided by the time. Okay. So obviously we know that the initial moles of oxygen are 0, right? Initial moles or volume of oxygen is 0 cm cube. Why? Because initially we just put hydrogen peroxide in the flask and now it is started to decompose. So now the amount of oxygen that's going to be formed, okay, we're going to calculate the moles of oxygen. So how do we calculate the moles of oxygen? Simple, moles equals to volume upon 24,000 because we're dealing with volume in cm cube. So 180 upon 24,000. 180 upon 24,000 and we get 0.0075 moles. 0.0075 moles. Now, do you guys realize one thing? If these many moles of oxygen are being formed, then double moles of H2O2 are going to decompose because the mole ratio is 2:1. So if these many moles of oxygen form, then multiplied by 2, double the moles of H2O2 are going to decompose. So for the moles of H2O2, we're going to multiply this value by 2. We're going to get the moles of H2O2, which are, so now from here we try to find the moles of H2O2, which are going to be 0.0075 times 2 equals to 0.015 moles. Now we have the moles of H2O2, which are 0.015. Now we just need the time. We know 90 seconds equals to how many minutes? 90 divided by 60, 1.5. So 90 divided by 60, we get 1.5 minutes. I don't think that needs any explanation. So 0.05 upon 1.5. Try it. 0.015 upon 1.5. And we get 0.01 mole. 0.01 mole per minute. I hope you got the working. First, we found out the moles of our oxygen gas. After finding out the moles of oxygen gas, we tried to find out the moles of H2O2 because their rate said change in the moles of H2O2. We know that the change is going to be equal to the moles of double the moles of oxygen because it's a 2:1. So we doubled the moles of oxygen, we got the moles of H2O2 that we knew we're gonna change. Now we had the moles of H2O2, we just divided by the time in minutes because they asked mole per minute, and that was 1.5 minutes, which was 90 seconds. So 0.015 was the change in moles divided by the time gave me 0.01, which was this option. Methanol is manufactured by reacting carbon dioxide and hydrogen together. Carbon dioxide plus hydrogen giving me methanol plus water. So that's a exothermic reaction. Okay, so heat is being released when we're making carbon dioxide and hydrogen react together to form methanol and water. What increases the equilibrium yield of methanol in this process? So we need a higher equilibrium yield. We don't care about the rate. So you should know that rate and equilibrium yields are two different things. Okay, so equilibrium yield only looks at the equilibrium. Increasing the pressure. So for pressure, we got to check out the number of moles. So if we have 3 plus 1 mole. 3 plus 1, we have a total of 4 moles on this side, and 1 plus 1. We have a total of 2 moles on this side. So we have 4 moles on this side and 2 moles on this side. When we increase the pressure, equilibrium shift towards the side that has less moles. So they say increasing the pressure. When we increase the pressure, equilibrium is going to move towards the forward side, the methanol side. And when equilibrium is going to move forward, we're going to form more of our methanol. And that is what we need. We got to form more of the methanol. So it's option number A. I hope you got it. That was easy enough. Adding an excess of steam. So if we increase the amount of steam, what's going to happen? The equilibrium, whatever we do, equilibrium tries to reverse it. So equilibrium will try to decrease it. And in order to decrease it, it's going to move backward to finish the excess steam. Adding a catalyst. Catalyst never affects the equilibrium yield. It only increases the rate. So no effect of catalyst. Increasing the temperature. If we increase the temperature, the forward reaction is exo and the backward reaction is endo. So if we increase the temperature, always remember whenever we increase the temperature, the equilibrium does the endothermic reaction. So it's going to move backwards, not forwards. So we wanted to move forward. The equation for the reaction of KClO3 is shown. So we have 4 moles of KClO3 that are forming KCl and KClO4. Which row is correct? Disproportionation reaction. For that, we got to check the oxidation numbers. So how do we figure out the oxidation numbers? For potassium, it's always a positive one because it's in group 1. For oxygen, it's going to be a -2. And then we see there are 3 oxygens. So -2 times 3. That gives me a -6. To balance out a -6, I need a +6. I already have a +1. How much more do I need on chlorine? I just need a +5 on chlorine. So that's my oxidation number of chlorine, potassium, and oxygen. In KCl, I know potassium is going to be a +1, chlorine is going to be a -1. In KClO4, I know potassium is going to be a +1, oxygen is going to be a -2, and since we have 4 oxygens, so -2 times 4, that gives me a -8. And to balance out a -8, I need a +8. I already have a +1. I only need a +7 more. So chlorine is going to be +7. Okay. So over here, I can see chlorine is changing from a +5 to a -1 and +7. Changing from a +5 to a -1. Okay, changing from a +5 to a -1. That's an example of reduction because your oxidation number is being reduced. And changing from a +5 to a +7, that's an example of oxidation because your oxidation number is increasing. So disproportionation reaction. Yes, this is a disproportionation reaction because in a disproportionation reaction, same species is being oxidized and reduced. Okay, so this is going to be an example of disproportionation reaction. Oxidation number of chlorine and KClO4, we just figured out it was a +7. So option number B. Okay, a student mixes 25 cm cube of 0.1 mole per dm cube sodium hydroxide solution with a 25 cm cube of 0.1 mole per dm cube hydrochloric acid, and the student records the temperature rise of 2.5 degrees Celsius. What is the enthalpy change of the reaction per mole of NaOH? Okay, so what are we gonna do? We're gonna form an equation. We know NaOH is gonna react with HCl to form NaCl plus H2O. That's a perfectly balanced equation. Now what we're gonna do, we're gonna figure out the moles of sodium hydroxide, which are 25 into 0.1 divided by 8,000. So I just figured out that I have 0.0025 moles of my NaOH, and that's going to be the same amount of moles of my HCl as well, because I have the same concentration in the same volume. Now the fact is that I have to calculate the enthalpy change of the reaction per mole of NaOH. I know that the energy that's going to be released is going to be equals to mc delta T. M is going to be the mass of my solution. 1 gram mass is of 1 cm cube solution. Over here I have 25 cm cube plus 25 cm cube. I have 25 cm cube of NaOH and 25 cm cube of HCl. 25 plus 25, which makes it 50 gram solution, times C is the specific heat capacity of water, which is 4.18, times delta T, which is the change in temperature. Change can be taken in degrees Celsius. Okay, change can be taken in degrees Celsius, because when you are going to convert change into Kelvin, that's going to be the same. So change is going to be 2.5 Kelvin. Degree Celsius change is the same thing. And this entire thing, let's see, what do we get? We get 50 into 4.18 into 2.5, and we get 522.5 joules. We have joules. Okay, we're gonna convert it into kilojoules. How do we convert joules into kilojoules? We divide by 1000. So 1 2 3, so it's 0.5225 kilojoules. But that's the amount of energy that's released when 0.0025 moles were reacted. I need the amount, the enthalpy change per mole. Per mole means when 1 mole is reacted. So how do I get for 1 mole? I say that when my 0.0025 moles were reacted, I got 0.5225 kilojoules energy. So when my 1 mole is going to react, I'm going to get X amount of energy. And what does my X come out to be? It comes out to be 0.5225 kilojoules divided by 0.0025 equals to, let's see, what do we get? Divided by 0.0025, and on my calculator I'm getting 209 kilojoules. Let's check, is our answer correct or not? 209 kilojoules per mole. Now you gotta be careful about this sign. Whenever your temperature is rising, you know your temperature is rising. Okay, and if your temperature is rising, just think about yourself. Is it gonna be a negative enthalpy change or a positive enthalpy change? Definitely a negative enthalpy change. Why a negative enthalpy change? Because your temperature is rising, you're releasing heat, and moreover, you should know this is a neutralization reaction we're dealing with. So it's negative 209. That's coming out to be my answer. Okay, over here, carbon monoxide and methanol can react together to form ethanoic acid. Okay, so that's a unique reaction we've never studied before, that we have carbon monoxide gas, we have methanol, and we're forming ethanol. We have a gas, we have a liquid, and then we have a liquid. And what's the delta HR? We don't know. Standard enthalpy changes of combustion are given in the table. What is the relative value for delta HR for the reaction between carbon monoxide and methanol? We definitely have to construct a Hess cycle. And how are we going to construct a Hess cycle? No worries. To construct a Hess cycle, first things first, we're going to put carbon monoxide here. Then we have methanol, which is CH3OH. And then we have CH3CO2H. Okay, now in the bottom, we are going to write carbon dioxide and water. Why carbon dioxide and water? Because we're combusting them. Combustion means obviously burning them and exhaust oxygen. So for when carbon monoxide is going to be combusted, 1 mole of it, we're going to form negative 283.0 kilojoules of energy. When methanol is going to be combusted, 1 mole, we're going to form negative 726.0 kilojoules of energy. And when ethanol is going to be combusted, 1 mole, we're going to release negative 874.1 kilojoules of energy. Now, we got to find our roots. We have to make 2 roots. The first root that I can think of is this root. Okay, it is this root. And the second root that I can think of, it's this root. Okay, the values that come in my second root are this and this, and the values that come in my first root are this and this. So now what do? This is my delta H of reaction. I equate my first and second root. How do you figure out roots? You just see from where all arrows are starting and where all arrows are ending, and then from where they're starting you make one root and then another root. Okay, so now what do we have to do? We have to write delta H naught of reaction R negative 874.1 equals to negative 283.0 negative 726.0. Let's see what we get. Delta H naught R equals to, you just rearrange it and open up your calculators, negative 283 negative 726 positive, because this 874 is going to go on that side and become positive. I guess that's elementary school maths. 874.1, and you get a negative 134.9 kilojoules per mole. Why? Because the values that were given in the table were in kilojoules per mole. So we are using all of them in kilojoules per mole. So I get negative 134.9. This is going to be my answer. I hope that's clear. This was easy enough. You just should know how do you make a Hess cycle and how do you make your alternative roots. Okay. I wish that we get a tricky question. I wish. Because the tricky questions are the ones from where you learn. Copper reacts with nitric acid under certain conditions. The products are copper 2 nitrate, water, and an oxide of nitrogen. Okay, so what are we doing? We're making copper react with nitric acid. So we have copper and we're making it react with HNO3, and we are forming copper 2 nitrate. So copper 2 nitrate means copper has a 2 plus. So we're going to take 2 nitrates. Plus we're forming water. Plus we're forming an oxide of nitrogen. So NXOX. Okay? OY. Sorry. NXOY. I don't know the values of my X and Y. 3 moles of copper react with exactly 8 moles of nitric acid. 3 moles of copper react with exactly 8 moles of nitric acid. 3 moles of copper react with 8 moles of nitric acid. So that's how the equation goes. What is the oxidation state of nitrogen in the oxide produced? First, we have to figure out the oxide. For that, we have to look at the products. So over here, the first things first, to balance out the equation, we got to balance out and then we got to write the products. We're going to put a 3 over here. Okay. And we got to put a 4 over here, where I'm just balancing it out. And now we have 3 2s are 6 nitrogens on this side and 8 on this side. So I need 2 nitrogens on this side. And how many oxygens do I need? I have 3 2s are, okay, 3 2 times 6, 6 times 3, 18. 18 oxygen plus 4 oxygen. What's 18 plus 4? That's 22 oxygens I have on this side. And how many oxygens on this side? 8 3s are 24 on this side and 22 on this side. That means I need 2 more oxygens on this side. So 2 oxygens I need. I need 2 nitrogens and I need 2 oxygens. So can I do this 2NO? Can I produce 2NO? Because you might think N2O2, but I've never seen anything like N2O2. So what I'm going to do instead, I'm going to produce 2NO. So the oxidation state of nitrogen in basically NO is going to be positive 2, because we know that oxygen is in negative 2. So to balance out, nitrogen has to be a positive 2, and I hope that makes sense. Oxygen negative 2, and nitrogen's got to be a positive 2 here. Okay, all the reactants and products, even if you make N2O2, even if you make this, okay, even if you make this, check out nitrogen's oxidation state. It's still gonna be a positive 2, even if you make this thing, okay? No worries. All the reactants and products of an exothermic reaction are gaseous. All the reactants and all the products are gaseous. Which statement about this reaction is correct? The total bond energy of the products, okay, which the reactants and products of an exothermic reaction, so heat energy is going to be released. The bond energy of the products is less, no, it's going to be more. The total bond energy of the products is less, no, it's going to be more. The total bond energy of the products is more than the total bond energy of the reactants, and delta H for the reaction is negative. Exactly what was in my mind. In an exothermic reaction, the bond energy of your products is more. Why is it more? Because more energy is released when those bonds are going to be formed. Okay, that's the concept of exothermic reactions. Propene, hydrogen cyanide, and carbon dioxide all contain pi bonds. Which molecule contains two pi bonds? So, first, let's draw propene. Propene is going to be carbon, double bonded to carbon, carbon, CH3, CH, and CH2. So that's the structure of propene. Which molecules contain two pi bonds? We can check that propene only contains one pi bond, and that's the pi bond. Hydrogen cyanide. Hydrogen cyanide is H bonded to C, triple bonded to N. We know that this bond is going to be a sigma bond. The first bond is going to be the sigma bond. The remaining two bonds are going to be your pi bonds. So it has two pi bonds. So hydrogen cyanide has, and carbon dioxide. The structure of carbon dioxide is going to be that you have one carbon double bonded to oxygen on this side and double bonded to oxygen on this side. You know that the first bond is your sigma bond and the second bond is going to be your pi bond. So we have two pi bonds here as well. So hydrogen cyanide and carbon dioxide only. Easy. Okay. Give us some difficult stuff, please. Q, R, and S are consecutive elements in period 3 of the periodic table. Element R has the highest first ionization energy and the lowest melting point of these three elements. R has the highest first ionization energy and the lowest melting point. Over here, the lowest melting point is going to be of sodium. R should have it. Magnesium, aluminum, and silicon. Highest melting point is going to be of S, so cross. Over here, silicon is going to have the highest melting point. Okay, R has the highest melting point. Over here, also silicon is going to have. So we wanted in which R has the highest. Wait a sec. No. Element R conductive. Lowest. Okay, sorry. In which element R has the lowest? Sorry, I thought the highest. Ionize and the lowest melting point. Okay, so in these three, the lowest is of sodium. So we want R to have the lowest, right? In these three, the lowest is of magnesium. We want R to have the lowest. In these three, the lowest is of phosphorus. We want R to have the lowest. In these three, the lowest is of phosphorus. So it's going to be option number D. I'm sorry, I thought the highest. Element R has the highest first ionization energy. Over here, phosphorus is going to have the highest first ionization energy. Why? Because from silicon to phosphorus, this is silicon, this is phosphorus, it is going to increase. But you know, from group 5 to group 6, there's a small dip. So there's going to be a small dip from phosphorus to sulfur. There's going to be a small dip over here. So that's why phosphorus has the highest. A reaction scheme for a group 2 metal M is shown. M reacts with oxygen, it forms X. X reacts with water, it forms Y. Then Y reacts with dilute sulfuric acid and forms E. That's going to be a group 2 salt. Which was correct, as M descends group 2 from magnesium, calcium, strontium, barium, radium. solubility of Y in water. So what is Y? Y is basically a hydroxide because, for example, you make magnesium react with oxygen, you form magnesium oxide, and then you make magnesium oxide react with water. What do you form? You form magnesium hydroxide. So the hydroxide descending group 2, you know that what happens to the solubility of hydroxide? It increases. So solubility of Y in water should increase. And now you're making the hydroxide react with sulfuric acid. So you're going to form a sulfate, right? So you're going to form magnesium sulfate over here. And what happens to the solubility of sulfate? It decreases. Got it? That was easy enough to understand. Okay, U, V, and W represent different halogens. So they represent different halogens: U negative, V negative, W negative. And then you have U2, V2, and W2. Okay, the table shows the results of 9 experiments in 9 aqueous solutions of U2, V2, W2 are separately added to separate aqueous solutions containing U negative, V negative, W negative, which row contains the ions U negative, V negative, W negative in order of their decreasing strength as a reducing agent. So if we talk about chloride, bromide, and iodide, what do you think is the best reducing agent? So this iodide is the best reducing agent, because what does a reducing agent do? Reducing agent loses electrons, and for iodide it is the easiest to lose electrons. So iodide is the best reducing agent. Which row contains U negative, V negative, W negative in order of their decreasing strength as a reducing agent? So strongest is gonna be the chlorine, then bromine, and then the weakest, because we're going in decreasing strength. In decreasing strength as a sorry. Look, that's how the question tricks you. So you have to, like, that's why I was just emphasizing the decreasing strength. So the strongest is going to be reducing agent is going to be iodide. So we're looking for iodide, then we're looking for bromide. The weakest reducing agent is going to be chloride. Decreasing strength is a reducing agent. So now when U2 reacts with U negative, there's no reaction. When U2 reacts with V negative, so let's just consider that V negative is this salt solution and U2 cannot displace it. So we know that U2 is less reactive than V negative, right? So U2, just let's write less reactive than V2. Okay, next we have V2. V2 can easily displace U negative. So V2 is more reactive, I just told you. Then V2 can easily displace W as well from its salt solution. So V2 more reactive than W. More reactive than W. Now we just need to know between W2 and U2. So W2 is more reactive than U2 because it can displace U2 from U negative. So W2 more reactive than U2. W2 more reactive than U2. So now we can displace which is the most reactive. V2 is the most reactive, then comes W2, and then comes U2. So V negative, W negative, and U negative. U negative is gonna be my iodide I'm considering, best reducing agent, and V negative is gonna be my chloride I'm considering. Okay, so according to my analogy, this is correct. J is either MgCl2 or AlCl3. No worries, we're gonna figure it out because of our qualitative analysis. And then you say that you don't learn qualitative analysis because you're given it in P3, right? Good, you're given in P3, but what for P1? You have to learn it. K is either SiO2 or SiCl4. That's easy, you just add water and you're going to figure it out because water is going to hydrolyze SiCl4. Okay, J, Add aqueous sodium hydroxide, you form white precipitates. Add an excess of aqueous sodium hydroxide, the precipitate dissolves. Okay, so we're dealing with aluminum here, I guess. Okay, we're dealing with aluminum 3 plus because in sodium hydroxide, aluminum precipitates dissolve. So I guess it's aluminum. And then K, add water, misty white fumes and white precipitate of solution. Yeah, what is going to happen is that when we add SiCl4 plus H2O, what happens is that SiO2 plus HCl 4 times this forms. Okay, so this thing is going to be SiCl4. This was an easy question. Okay, you just had to learn the qualitative analysis and your reaction. River water in an agriculture areas contain ammonium carbonate, hydrogen carbonate, chloride, and NO3 negative 1. HNO3. Nitratines, not nitritines. Nitrites are NO2 negative 1. This water is treated by adding calculated quantity of calcium hydroxide. What is precipitated from the river water when the calcium hydroxide is going to be added? Calcium carbonate. Am I wrong about it? Let's see. No, I'm not wrong. Because I know that ammonium salts all are soluble, all nitrates are soluble, calcium chloride is soluble because all halides except silver and lead are soluble. Elementary school math, not math, elementary school chemistry. Calcium carbonate insoluble. 4 atmospheric pollutants are listed: nitrogen oxides, carbon monoxide, unburnt hydrocarbons, and sulfur dioxide. Which pair of pollutants react to form peroxyacetyl nitrate? Oh my god. So such a difficult question. Nitrogen oxides and unburnt hydrocarbons 1 and 3. That's so easy, mashallah. Which graph correctly describes the trend found in group 17? Please give difficult questions. I guess I should write a report to examiner that give good questions. Bond length in X2. Bond length is going to increase. Why? Because you know that the size of chlorine is this. If the size of chlorine is this, so that's the bond length of chlorine. But the size of bromine is going to be greater than that of chlorine, something like this. So the bond length is going to increase. And then if we talk about iodine, the size of iodine is going to be even greater, something like this. So the bond length is further going to increase. Okay, so over here this is a cross, it doesn't decrease, it increases. This is a cross, it should be greatest for iodine. Okay, so that's about bond length. Okay, that's a cross. I didn't read. Let's see other things as well. Boiling point of X2. You know that the highest boiling point is going to be of iodine because iodine has the strongest IMFs. And what kind of IMFs does iodine has? It has van der Waal forces. And why does it has the strongest? Because it has the highest number of your electrons, so that's a cross. Iodine should have the greatest, and van der Waal forces iodine greatest. Option number B we go with. And then bond energy is going to be greatest for HCl. Why? Because that's going to be the strongest. Gas M is produced when ammonium chloride is heated with calcium oxide. You should know that whenever we heat an ammonium salt with any kind of alkali, what do we produce and what kind of reaction is that? Okay, first things first. So let's see what's happening inside the reaction. Just like rote learning that ammonium salt and alkali is going to give you ammonia gas is not going to make things good. So let's look what's happening. So you have this ammonium salt, which is ammonium chloride, and you make it heat with an alkali, which is CaO. First thing, you're going to form CaCl2, which is a salt. Second thing, you're going to form H2O, which is water. And the third thing you're going to form is ammonia, which is NH3. Now what's happening is that If you look at the oxidation states, no oxidation state is changing in this reaction. Look, no oxidation state is changing. And you can see, look, if you don't believe me, nitrogen is a negative 3 here, hydrogen is a positive 1 here, chlorine is a negative 1 here, calcium is a positive 2 here, oxygen is a negative 2 here, calcium is a positive 2 here, chlorine is again a negative 1, hydrogen is again a positive 1, oxygen negative 2, nitrogen negative 3, and hydrogen positive 1. Check it for yourself if you don't believe me. No oxidation state is changing. Then if it's not a redox reaction, you might think, oh, how in this universe can ammonium chloride be an acid? Well, it's an acid. Why? Because in O-levels IGCSE we used to learn that acids are those that give hydrogen ions. Yeah, acids are proton donors. And look what ammonium is doing. It's donating its proton, giving its proton to this thing and forming ammonia. Ammonium NH4 plus donated its proton to form NH3. Ammonium is an acid because it donates its proton, and calcium oxide is a base because it's a proton acceptor. The oxygen over here accepted the proton and formed water. So well, this is an example of an acid-base reaction. Okay, so acid base, and the identity of M, I told you the gas we form is ammonia gas. So that's the reaction happening. Okay. Two nitrates decompose on heating according to the equation shown. Lead nitrate, lead oxide, nitrogen dioxide, oxygen, ammonium nitrate forming nitrogen, oxygen, and water. 1 mole of each nitrate is heated separately. The gas produced in each reaction is bubbled through NaOH. Now, what kind of gases are we bubbling? We have NO2 and oxygen. Okay, and over here we have oxygen and nitrogen. Oxygen and nitrogen are neutral gases. So even if we bubble them through NaOH, no reaction is going to take place. But over here, look, NO2 is an acidic gas. And if we bubble an acidic gas through NaOH, what's going to happen? Probably you're going to form a salt, right? The volume of any gas that does not react with NaOH is then collected and measured. Which nitrate shows the greater percentage loss in mass and produces the greater volume of gas collected? The greater volume of gas collected is gonna be over here in ammonium nitrate, because over here this NO2 is gonna react. So over here only 1 mole is gonna be formed. Over here 2 plus 1, 3 moles of gas. So the greater volume of gas is indeed gonna be in ammonium nitrate. Okay, ammonium nitrate. Greater percentage loss of mass. Okay, the volume of any gas that does not react with NaOH is then collected. Measure which nitrate shows the greater percentage loss in mass. 1 mole of each nitrate is heated separately. So greater percentage loss in mass. So we're losing mass when we form solid. That's the mass that's being restored. And when we form gas, we lose mass, right? So how much if we take 1 mole of this and 1 mole of this, right? How much we're going to have 2 moles of this, half mole of this, 1 mole of this, half mole of this, okay? Now look, the mass of 1 mole of lead nitrate is going to be, let's go to the product table, check out the mass of lead, and then we're going to figure out. So lead is PB. Where's PB? Lead. 207.2. 14 plus 16 times 6. So the mass of this thing comes out to be 331.2. And the mass lost is going to be 2 times of NO2. So 2 times the mass of NO2, which is going to be 14 plus 16 plus 16. That is 92 plus half times oxygen is going to be 16. So 16 plus 92, that's the loss. 108 upon 331.2 times 100%. Let's check out what's the percentage loss. Okay, they've not asked about the total loss. They've asked about the percentage. That's why we have to calculate the percentage. because otherwise, just by seeing it, we can tell the greatest loss mass is going to be here. But the percentage loss mass greater might be over here. We don't know. So don't do this mistake. We get 32.6% here. Now let's see what we get here. We gotta have the mass of ammonium nitrate, which is gonna be 14 plus 14 plus 4 plus 16 plus 16 plus 16. That gives me a 90. No, not a 90, an 80. And now we need the mass of 1 mole of nitrogen, which is 14 plus 14 plus half of oxygen, which is 16. That's 44 times 100. Do it. Do the maths. 44 upon 80 times 100, and we get 55%. I told you na, the greater mass loss is here, but the greater percentage by mass loss is here. Now look at the words. Look at the trick the examiner is trying to play. He just said the greater percentage loss of mass. Though greater loss is over here of mass, but greater percentage loss is over here. So that's why it's this option. That was a very clever question, I'd say. Okay, organic compound X has the empirical formula C2H4O. Compound X is reduced by LiLH4 but not NaBH4. I guess that's a very big green, red flag, whatever you say, okay, it's not being reduced by NaBH4. What do we know? That what kind of compounds don't get reduced? Acids. So we're going to consider our ethanoic acid and our butanoic acid. So ethanol and butanol crossed. Now, second thing, we got to check out the empirical formula. For ethanoic acid, it's C2H4O2. And for butanoic acid, it's C4H8O2. That's the molecular formula. Now, if we convert it into the empirical formula, what do? We just cut 2 1 times 2, 2 2 times 2 1 times. So that becomes CH2O. If we cut here, 2 1 times 2, 2 4 times 2 4 times 8, and 2 2 times 4. So C2H4O. So over here, that's the empirical formula for butanoic acid. Okay, that's the empirical formula for butanoic acid. So that means the correct answer is going to be butanoic acid. What is the mechanism for the reaction of hydrogen cyanide with propane on? Nucleophilic addition. Am I correct or not? Let me check. Yeah, that's nucleophilic addition. Like, you don't need to think about it. You know what's propane on. Propane on means carbon, 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 double bonded O, hydrogen, 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 hydrogen. And now what's going to happen? A cyanide ion, something like this, and with an H is going to attack this. This is partial positive, this is partial negative. This cyanide ion is going to break off from here and attach over here, make a bond with this carbon, and this double bond is going to break from here, and this hydrogen that's over here is now going to make a bond with this OH. So what's this? A nucleophile is being basically added. So that's nucleophilic addition. Okay, no worries. Which compound may be synthesized from an alkene with the formula C4H8 by an addition reaction? Okay. Which compound may be synthesized from an alkene with the formula C4H8? Okay, with an alkene, which compound may be synthesized from an alkene? We have to make it from an alkene with the formula C4H8 by an addition reaction. Okay, 1,1-dibromobutane. Okay, so first I need to understand what the question is trying to say. Which compound may be synthesized by an alkene? So the alkene is C4H8 and we have to do addition in it. So it's something like this maybe. C4H8. And now we got to see that can we do addition in it? 1,1-dibromobutane. So if I add bromine into it, 1 bromine here, 1 bromine here, that's 1,1-dibromobutane. Well, that's not technically possible. Why is this not possible? Simple. It's simple. You cannot add a bromine here and here. Why can't you add 2 bromines like this? Because, look, if you're breaking this bond, you have to attach one bromine to this carbon and one bromine to this carbon. You can't just break a bond and attach both bromines to this carbon. Well, that doesn't make sense. 1,2-dibromobutane. So you break this bond, attach one bromine here, attach one bromine here. Well, that makes sense. So this makes sense to me. Let's check the next option. 1,3-dibromobutane, like one bromine here and one bromine here. How is that possible? How can the first and third carbon have a double bond? It's impossible to have a double bond between the first and the third carbon. 1,3-dibromomethylpropane. Again, impossible to have a double bond between the first and the third carbon. Okay, the structure of compound G is shown. So this is compound G. G undergoes addition polymerization, which diagram shows the repeat unit of the polymer formed. So where do we have to do addition polymerization? Here, here, or here? Obviously on the carbon, double bonded carbon. So if I were to make a polymer of it, what would I do? Carbon, extension bond, bonded to hydrogen, double bonded to carbon, triple bonded to nitrogen, bonded to carbon, double bonded to O, bonded to C, H, and H. And then there is like a bond here, and then this. That's the repeat unit. Where do I see this? No. What kind of stuff is this? CO2CH3. But like, why would you do polymerization here? You do it on carbon double bond. So that's exactly what I've made. They've just condensed this thing. They've condensed this entire thing to this thing. That's what they've done. Otherwise, we're the same, and they've condensed this thing to this thing. Okay. Compound T is tested with 3 reagents and gives the results shown. 2,4-DNPH, orange precipitate, Felling solution, no reaction, acidified K2CO2, no reaction. Well, what are we dealing with? I guess that's as easy as ABC, that we're dealing with a ketone. So we got to find a ketone over here. Where do I see a ketone? Well, I just see them and I know this is a ketone because I can see a carbon, double bonded carbon in the center. Over here, I can see it at with an OH. Well, that's not a functional group. Look. A second. Let me draw C as well. Well, this compound is going to react with acidified K2Cr2O7. Why? Though it has a ketone group and it's going to give you 2,4-DNPH orange precipitate, but it's also going to react with acidified K2Cr2O7. So, because of this OH, so they say it doesn't react. Then over here, we again have an OH. Over here, we have an aldehyde. Aldehyde is going to give you a positive Felling's test. Okay. Reagent X is added separately to 2-methylbutane 1-ol and 3-methylbutane 2-ol. The visible results are different. What is reagent X? Okay, let's draw the structure. So 2-methylbutane 1-ol. 1, 2, 3, 4. That's butane. Now on the second one, we have a methyl. That's 2-methylbutane 1-ol. 2-methylbutane 1-ol. 2-methylbutane 1-ol. Okay. And then 3-methylbutane 2-ol. 1, 2, 3, 4. 3-methylbutane 2-ol. Oh my god. You know which reagent is going to give you a different test? Look. Can you see something strange over here? Look at this thing. Look. Can you identify this functional group? What kind of group is this? This is a COHHCH3. Well, this is going to give you a positive iodoform test, and this is not going to give you an iodoform test. So, do we have alkaline I2? Yeah, we have. And we are correct. whenever you have C double bond O, CH3, this gives you a what does this give you? A positive iodoform test. And this group also gives you a positive iodoform test. So I always tell people not to remember like methyl alcohols and that stuff, and this stuff is going to give you test. Just learn the groups that are going to give you like a positive test. Okay. Compound Y is hydrolyzed by warm aqueous silver nitrate to form a precipitate that is soluble in aqueous ammonia. Compound Y undergoes the elimination reaction to form an alkene. What is the skeletal formula of compound Y? Definitely not iodine, right? Definitely not bromine, because that's soluble in dilute aqueous ammonia. So we're dealing with this or this. Now compound Y undergoes elimination reaction. Elimination means that you can take out the halogen from the alpha carbon and hydrogen from the beta carbon to make a alkene. So over here, this is my alpha carbon. Okay, so this is my alpha carbon and this is my beta carbon. My beta carbon has 2 hydrogens. So if I take out chlorine from my alpha carbon and this hydrogen from my beta carbon, what's going to be left behind? There's going to be a double bond over here. So done. Why not this? Because look, this is alpha carbon and this is beta carbon. Can you see one thing over here? Beta carbon has no hydrogen, so you cannot take out any hydrogen from the beta carbon. You can take out chlorine from the alpha carbon, but how are you going to take hydrogen out from the beta carbon? Because this one's alpha and this one's beta. You can't take out. That's why it's option number C. Propane 2-ol can be converted to 2-chloropropane. Propane 2-ol can be converted to 2-chloropropane using reagent M followed by reagent N. What is the correct? Okay, so if propane 2-ol, carbon, 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 OH, H, 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 H. Concentrated NaOH followed by Cl2. Well, you don't have to add Cl2, because if you add Cl2, what's going to happen? If you add Cl2 to it, then it's not going to work out. First, you have to convert it to an alkene, and you only convert it to an alkene by a strong acid. So what do? You're going to convert it to an alkene. You're going to remove this, and then it becomes an alkene. And now what do? Now you add HCl to it. Now what's going to happen? This alkene, electrophilic addition is going to take place, because alkene plus obviously this substance, this double bond is going to break, and H is going to be attached here and Cl going to be attached here, and now you form 2-chloropropane. So it's this. Why using H3PO4? Because any strong acid can do your dehydration work. Like you want to remove the OH, you want to do the dehydration, any acid can do it. Skeletal formula for organic compounds are shown. Good. This is a aldehyde, this is a ester, this is a nitrile, this is a ester again. Which two compounds, when separately heated with dilute sulfuric acid, produce propanoic acid as one of the products? You break it from here, carbon, carbon, carbon. This is going to form propanoic acid, ester, hydrolysis. This is a nitrile. Hydrolysis of a nitrile forms an acid. Carbon, carbon, carbon going to form propanoic acid. So option 2 and 3. This is going to form what kind of acid? Ethanoic acid. And what kind of alcohol? Propanol. What is this going to form? Well, this is going to get, this is not going to form anything with acid, right? This is going to get oxidized. So with sulfuric acid, it's 2 and 3, right? Yeah. Okay. 1-chloro-2-methylpropane. 1-chloro-2-methylpropane. Oh my god, that's such a big name. 2-bromo-2-methylbutane reacts separately with aqueous silver nitrate and ethanol. Reacts separately with aqueous silver nitrate and ethanol. Both reactions proceed via nucleophilic substitution. Both reactions proceed via nucleophilic substitution and a precipitate is formed. Okay. The time taken for 1-chloro-2-methyl propane to form precipitate is T1. So let's just draw it instead of reading out the names again and again and making yourself feel bad. So it's propane in the main chain, 1, 2, 3. Then it's 2 methyl. So 2 methyl and 1 chloro. Well, you can see that's a primary halogenoalkane. You can see it's primary. I don't think I need to explain this even, because you can see hydrogen and hydrogen with a carbon that's bonded to chlorine. Now we draw 2-bromo-2-methyl butane. So butane means 1, 2, 3, 4, 2-methyl and 2-bromo. You can see what is this. I don't think that needs any explanation. This is simply tertiary halogenoalkane. Okay, compound the time taken for 2-bromo-2-methyl is T2, which was correct. So this 2-bromo-2-methyl is going to do SN1 mechanism. SN1. Okay, so this is going to do SN1 and 1-chloro is going to do SN2 mechanism. But over here we don't have to check the SN1 and SN2. For the precipitate to form, we have to check the bromide and the chloride. You know that bromide precipitates are going to first. So bromide are forming in this T2. So T2 is going to be smaller and T1 is going to be greater, because chloride precipitates are going to form later, because carbon chlorine bond and carbon bromine bond, there's a difference. Carbon chlorine bond is stronger, carbon bromine bond is weaker, so precipitate is going to form faster. The diagram shows a structure of progesterone. Which statement about progesterone is correct? Okay, so one molecule contains 4 chiral carbon atoms only. Let's calculate the chiral carbon. 1 chiral, 2 chiral, 3 chiral, 4 chiral, 5, 6. Do we have any more? Do we have any more? Let me check. 1, 2, 3, 4, 5, 6. I could just figure out 6. So one molecule has 6 chiral carbon atoms, and the molecular formula is C19, C21. Let's calculate, just count the number of carbon atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. 21. Option D. I guess that was fairly easy enough. A molecule of hexane can be cracked in a number of different ways. The compounds are listed: C3H8, C4H8, and C5H12. Which compounds are found in the mixture of products from the cracking of hexane molecules? So if you're going to crack hexane, which compounds are found in the mixture of products from the cracking of hexane? I guess 1, 2, 3 all. But hexane is C6H14. If you form this C5H12, just think for a second, if you form C5H12, what are you left with? CH2. CH2 is not an existing compound. Look, you're only left with CH2. You have to make an alkene. That's why this thing is not going to be formed. Got it? You can form an alkene or an alkene and hydrogen. Alkene and hydrogen. So that's the thing. That's why this cannot be formed, because otherwise you would have to form CH2, which is not possible. So 1 and 2. The diagram shows the structures of 2 isomeric dicarboxylic acids, X and Y. So the unique thing about the structure is that in the center we have a carbon double bonded carbon. On the upper side we have a carboxylic group like this, and we have 2 carboxylic groups on this side, right? So this is basically cis and this is trans. And we have this compound with the empirical formula. This X and Y are going to become the same thing, because when they two are isomers and you add something to it, they both are going to become the same thing. So compound P and Q are identical. They're going to be identical once we reduce them. What is the total number of sp3 hybridized atomic orbitals used in the bonding of butene? Okay, carbon, 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 and now we have to tell the sp3 atomic orbitals that are used in the bonding. So this carbon is sp3 hybridized. This orbital is sp3 hybridized. 2 orbital, 3 orbital, 4. 4 sp3 hybridized orbitals of this carbon. What is the total number of sp3 hybridized? Then 1 sp hybrid sp no, this orbital of this carbon is going to be sp2. This is going to be sp2. Okay, this is going to be sp2. Then this one is going to be sp2, and this one is going to be unhybridized. Then we come to this carbon. This carbon is also going to have sp2 hybridized orbital, sp2, sp2 and sp2. How do I know this? Because it's making 3 angles and it has a double bond, so it's sp2 hybridized. And then we come to this carbon. The last carbon is also making sp3 hybridized because it's single bonded. So how many in total sp3 hybridized? We have 1, 2, 3, 4, 5, 6, 7, 8. 4 for this carbon, 4 for this carbon. So in total 8 sp3 hybridized. Compound L contains carbon atoms. It is analyzed in the mass spectrometer. The table shows the relative abundance of the two peaks recorded. Mass to charge ratio greater than 127. Okay, 128 and we have 129. How many carbon atoms are present in a molecule of L? The formula is very simple upon here, like 100 upon 1.1 into the abundance of R, m plus 1 peak, right? M plus 1 peak, and upon the abundance of our m plus peak. So that's how we're gonna figure it out. So m plus 1 and m peak, we take the ratios. Over here, we know that 128 plus 1 is going to be 129, right? So 129 is going to be a m plus 1 peak, which is going to come over here, the abundance of which, and 128 is going to be our m peak. So it's going to be 100 upon 1.1 into m plus 1 abundance, which is 5.5 upon 50, which is going to be the abundance of the m peak. And let's do it on calculator. 100 into 5.5, so a 100 into 5.5, we get 550. So 550 divided by 1.1 into 50, we get 55. So that's 550 upon 55, 550 divided by 55, and that gives me 10. So I have 10 number of carbon atoms. The only thing is that you have to learn the formula 100 upon 1.1 multiplied by the abundance of your m plus 1 peak upon the abundance of your m peak. That's all.